Hello, welcome to the first video for the first unit matter that will cover chapters 1, 2, and 3 of your iBook. As you've already downloaded it, that's where you are most likely seeing these notes as well. This video will focus mainly on chapter 1, chemistry and the nature of science. We can define science a number of different ways. The very formal definition of science is a methodical exploration of nature, followed by a logical explanation of the observations. So what does that mean? That means that we are taking our time to explore the world around us, and then trying to explain what we saw from a logical way, in a way that makes sense to us. Chemistry is the study of that world around us, but more specifically the materials and the changes that they undergo. And that is why we look at chemistry as, well, as we'll see, one of the more central sciences, meaning everything is there. The air that we breathe, the water that we drink, the clothes that we wear. It makes us us. There's a certain specific chemistry that we look at. And so for us, chemistry is an extremely important part of our everyday life. You would not be able to watch this video if it was not for chemistry, be the battery and the materials that have gone into making the battery, to make the iPad, to make your smartphones, to make your car run. Traditionally, there are 4 areas in chemistry. There are usually subdivisions of each of these. Each one will be looked at in some manner in this class. We will focus most of our time on the inorganic part of chemistry. A little bit of physical chemistry, that usually tends to be gas laws and thermodynamics. Those are things that will come in the second semester. We will look at a little bit of organic chemistry that we will see when we look into naming covalent compounds, what makes covalent compounds be there, and there's some real good real-world applications of them. And then very small amount will be looked at for biochemistry, as that is one that takes what you've actually looked at already in your biology class, where you looked at how the chemical reactions within the cell, such as the Krebs cycle and photosynthesis, or even some of those are just examples. We will look at more specific areas within each of these, and we really just try to introduce you to a lot of these ideas, chemistry concepts that have this, and you'll find that there's a lot of real-world application of this chemistry and science around you. Here's the first question that we will pose, and that is what are the traditional areas of study mostly involve? The organic chemistry, inorganic chemistry, and biochemistry. Some of these answers might be found in your notes, or might even be found from reading your chapters. Why study chemistry? Well, it is sometimes called the central science because, well, it overlaps with a lot of different disciplines. Biology would not be able to explain DNA without the fact that it is a chemical compound made of atoms, and we will be looking at that later on. Minerals that you studied back most likely in 8th grade physical science, or 8th grade earth science, they have a chemical compounds again, and they're very specific. Some of them are just a slight change within the addition of a magnesium or exchanging a sodium for a potassium will give it different properties, and that's extremely important. Elements that are used to run nuclear power plants use uranium, and that is a lot of physics that goes on to that. Nuclear physics and nuclear chemistry is done because of what we look at. So where else can we find ties to chemistry? In agriculture, a very common industry in this area, we use that to make sure that you're using the proper pesticides and or fertilizers. If you don't use pesticides, you have to, you are susceptible to potential bugs of some sort. But if you don't use fertilizers, you can also not grow as high a yield. And the fertilizers that you use, are you using a natural fertilizer or are you using more of a synthetic fertilizer? Each of them have a chemical compound. Each of them you're trying to add nitrogen into the soil. Why in agriculture we see that crop rotation is an important part of what we do. The petroleum industry is highly use of chemistry. It is the using of the separation of crude oil, development of gasoline, mixtures, additives, other byproducts that we use from the petroleum industry. It is not all just gasoline, diesel, jet fuel that we get from petroleum that we pump out of the ground. It comes and goes into a lot of different things, and we will look at that specifically in a later unit. In medicine, instruments that are used for testing to develop medicines, treatment of diseases, the materials that they're actually using, why you use a stainless steel chrome finish item, how that actually is done is some pretty good chemistry. The chemistry of just the medicine itself is pretty intense as well. Not all of this will go into in depth in those ways. One could look and read and become more knowledgeable of. Instead, we are trying to give you a basic background of that. In our daily lives, why are we not supposed to mix toilet bowl cleaner and bleach? Well, there's some byproducts of that, or Drano and bleach, or some things that we're not supposed to use. Ammonia and bleach is really what the bad one is. Why does baking soda and vinegar react? Why does baking soda and a slight amount of vinegar actually help clean? Why does just vinegar clean some of the hard water stains or hard water marks that we have around our faucets? Those are chemistry in our everyday life, and that's the chemistry that I find enjoyable. To start going through some of the history of chemistry and or science, ancient Egypt gave us a lot of math. Ancient Greece is looked at to give us more of our scientists, our philosophers, and very early ones gave us what's known as alchemy, where the first elements that were given are the earth, water, wind, and fire, which is actually the element brands parts of their element, and that is kind of humorous, and that they use that. It's an alchemy idea. More elements were added later through their investigations, but alchemy was, for the most part, a predecessor to chemistry. It came before chemistry. And alchemists are more widely known for their abilities, or lack thereof, to try and turn lead into gold. Although never able to do that, but it's the methodology that they use, the trial and error processing that they did, gave us what we now look at. John Dalton is looked as a British school teacher, kind of gave us what we seem to be more describe the scientific method as a systematic approach to explaining phenomenon. I like a very simple scientific method. There are some scientific methods out there that will go over 7 to 9 steps of the scientific method, but ultimately I think it really does boil down to these methods. where you have an observation. And from that observation, you create a hypothesis. And from that hypothesis, you revise it based on your experimental data that you need to go into. So when you go from an observation to your hypothesis, you then move into an experiment. That experiment needs to be testable based on what you wrote as your hypothesis. The majority of time spent in science is actually in those going from hypothesis to experiment and experiment to rewrite your hypothesis, back to your experiment again to test your rewritten hypothesis, and then back to your hypothesis whether or not it happens. Very rarely do you go from hypothesis to experiment to a theory or even to a law. Some theories are just end at there because even if you have some experimental evidence to prove it, you still need to kind of go back and forth by definition, as we'll see a little bit later, of what a theory is and what a law is. And sometimes some theories are just probably better kept as a theory. As we don't have a scientific law to write out why the moon exists, we have theories of why the moon exists or how it came to exist. Experimental evidence to try and show that, well, that's going to be very difficult to do, being as that nobody was around when that probably happened. So it's a step process that we go through. A hypothesis is not just an educated guess that explains an observation. The part is it explains an observation. Not all hypotheses are correct. If anything, majority of them are incorrect. We need to write them in a way that they can be testable, though. That is the important thing, is that our hypothesis needs to be written in a way that it can be changed if the experiment doesn't agree with the hypothesis. So you need to be able to adjust, change as it is there. You can't just go, well, I think this happens. No, if you start a hypothesis, I think, I guess, that is a bad hypothesis from the go. It needs to be a testable statement. A statement does not have I guess, I think. Those are guesses and thinking and ideas, not a hypothesis, a statement. An observation might be you taking two clear liquids that are mixed and a solid forms. And that solid is a precipitate, but not knowing anything about the clear liquids, you might not know. Upon further investigation of what the liquids are, you find that they contain calcium and sodium. And so a hypothesis would be when solutions containing calcium and sodium compounds are mixed, a solid forms. Well, one way to test this would be actually taking a testable way of saying, okay, I take calcium, say chloride, and mixing it with sodium chloride solution, mixing those two, and you would find that nothing happens. Instead, so therefore, you've tested it. So it doesn't actually mean that it has to be calcium. It's not calcium and sodium that makes that solid form. It's something else. And so then you would go back and retest. A bad hypothesis is two clear liquids are mixed and a solid forms. Well, I can take water and vinegar and no solid's ever going to form from that. But those are two clear liquids, and that's terrible. You can't, what two liquids? So by having something a little bit more specific, say something that has calcium and sodium compounds mixed, does a solid form. In some cases, it will. In some cases, it won't. But that's the part of the process. Here is our second let's think about it question. A hypothesis is what? So experiments, they are controlled testing of the properties, so we need to control them as much as we can. We can't control everything in the lab, especially in a high school lab. Very difficult to control every single variable that we have, and variables are things that can change during the experiment. You have two types, one that's manipulated, one that is responding. The responding variable is dependent upon what you've changed. An example would be if all of a sudden your data that you use, regardless whether or not you have unlimited or not, was cut down to 1 gigabyte. That's the variable that has changed. Is that the manipulated variable or the responding variable? Changing your data would actually be the manipulated variable. Now, how you respond to that is probably overcharging, becoming irate because you no longer have the same amount of data anymore, potentially having to forced different ways of being on social media. But those would be kind of what you're looking at. What are you changing? What are you keeping the same? What is going to change? What are you looking at? Now, the scientific method can't be applied to all situations because the variables that can change over the course of an experiment. In the classroom, sometimes temperature can change a little bit, depending if we're using the Bunsen burners a lot. The atmospheric pressure, we are susceptible to those atmospheric changes as the day goes on. So as we look through the day, the weather's going to change, and that can have an effect on certain things. That's why we have barometers, so we can take readings of what it is at this time. So those kind of help us look at some things as long as they're measurable. The scientific method can't be applied to, say, the stock market, as the financial planning cartoon here indicates. That, even with the crystal ball, but you might not know how it works. There are too many variables that are uncontrollable. So the stock market is just one example where scientific method isn't going to help. You can use a lot of data over a lot of time to help you make guesses, especially in the stock market, but it's not going to give you that full finished product. The differences between theories and laws lies in their definition. A general explanation, that is I think, one of the most important parts. It is a general explanation. Usually it's through some model or to explain things. Scientific law are statements or equations that explains the scientific concept. They're statements and equations. Yes, they kind of explain something, but usually theories are more of a done through a model, a much more in-depth explanation of the why something maybe is happening. Scientific law is this happens because this usually. So you're describing that observed behavior. Doesn't say why the behavior happened. It just says this is what happens. Gravity. Objects fall because of gravity. How they fall, what happens, some of those types of things, how you can slow it down. Those are other variables that would be taken into account. One of the fundamental laws that we use in chemistry, we will bring this up again, is the law of conservation of mass. It has changed over the last 100 years, and so we look at it as the law of conservation of mass states that during an ordinary chemical reaction, the total mass of the substances don't change, meaning what you start with should have the same mass with what you end with, as long as you're keeping all variables taken into account. Doesn't explain what's happening during a chemical change because all the chemical changes can be different, as we'll see later on. It just says the mass needs to stay the same. You could even have it more mathematical in nature, but we'll forego using the math part of it at this time. Theories, however, can give us the what things look at in extremely small scales. The atom, we have a lot of good theories because we don't know everything that's going on with the atom. We know a lot, and we can use some scientific data to help prove that these atoms do exist. But how they look, we can use, again, some math, some experimental evidence. But what is actually happening, we'll start to use analogies, and that will become very prominent in one of our later units of how does this actually work as we move forward. So atoms and molecules, they're treated as hard spheres. They are not hard spheres, but we treat them as hard spheres so that they can kind of see what they might look like. Is we kind of see a kind of a shading of a hydrogen atom here, and from here you can see what it looks like is it's ethane, because you have a carbon atom, and using the same blues, a hydrogen, hydrogen, and a hydrogen there. There's a hydrogen there. There's another hydrogen hiding back there. Kind of tough to see it. But that's what an ethane would look like. You have a carbon-to-carbon bond with each carbon having 3 hydrogens around it. That's one way it can look at. We will look at what it looks like in a later unit from a different perspective using a different set of models. Here is our third let's think about it question. Lavoisier is credited with transforming chemistry from a science of observation to a science of Now, why do scientists choose to collaborate? Why is collaboration an important part of chemistry and science? Because some research problems are tough and not everybody has all the answers. We might think that we have all the answers. I might think I have a lot of the answers as a parent or as a teacher, but I don't have all the answers. I need to collaborate with my colleagues in the science department or outside of the science department. And in other means, when I would do research, you collaborated because maybe I have an idea or a thought that might help and explain your idea or thought, or maybe I have some resources such as a piece of equipment that you need to run that I have, but you have a piece of equipment that I need to run some experiments on, and so you kind of do an exchange of means for that. As a kind of a ways of, hey, do this for me. How this is done is changed and evolves over time. As we look at this, how these ideas are given out, you can go to research presentations, read papers. How this collaboration usually happens are people will go to a talk and they think that, hey, I might have an explanation of why you're seeing that, and usually these relationships are put there so that they can get to the answers of the questions that they have. Why are articles in scientific journals the most reliable source of information about new scientific discoveries? Is our fourth and final question of this chapter.